Welcome back. Our prior video introduced the intuition behind sensitivity analysis and partial identification as a way to overcome the shortcomings of selection on observables OLS. And in this video, I wanted to go through 3 different papers that have attempted to operationalize the ideas that we introduced in the prior video and think about how these things can be applied practically. And hopefully this will give you a little more intuition regarding how this mindset can help you to make better empirical conclusions. And we'll start back in 2005 in the Journal of Political Economy. And in this paper, Joe Altonji, Todd Elder, and Chris Taber wanted to analyze the effect of attending a Catholic high school on later life outcomes. And this is the pioneering paper for thinking about this approach to partial identification. I will say that this paper has nearly 5,000 citations on Google Scholar. That's roughly 4 times my lifetime citation to date. So this is a very foundational and popular paper that's been cited far and wide. And like I said, they want to estimate the causal effect of attending a Catholic high school. But of course, this is not something that we can really randomize, and there's a lot of selection into who goes to a Catholic high school. And if you read through their paper, they go through a lot of different arguments and eventually settle on the idea that we should have equal correlation between D and X beta versus D and epsilon. And one of their key ideas for thinking about why this equal correlation restriction makes sense has to do with how data is collected. If we think about how X compares to the whole set of factors that could affect our outcome, we're only seeing a subset of that in X. And typically in household surveys like the one that they used in their paper, data is collected for multiple purposes. It's also costly to collect, and some variables are just impossible to measure. And so in the end, they argue that X is a random subset of everything that affects Y. And so for that reason, we would expect these correlations between D and epsilon and D and X beta to be equal. Of course, this is just an assumption, and we could certainly do a simulation where we have it be the case that X contains most of the relevant factors, in which case we would probably want correlation between D and epsilon to be much smaller than correlation between D and X beta. Or we could have the opposite, where X only contains a few components that are relevant for Y, in which case we would want this condition to be such that correlation between D and epsilon is much larger than correlation between D and X beta. So the thing I like about these types of approaches is that it makes you think about, well, how is my data gathered? What does my actual data generating process look like? And that can be illustrative even if you're not wanting to do this as your final analysis. I view this as formalizing the logic that every applied econometrics researcher should be having when they're evaluating their analysis. So as I was saying, the amount of correlation that we're assuming between D and epsilon versus D and X beta is going to be application specific. And so we need to think about what are the sources of the bias? Why is our R squared so low? Is our R squared low because there's just a lot of noise in the process that generates Y? Or is it so low because we're only picking up some small subset of all of the factors that affect Y? And so this makes us think about measurement error. It makes us think about irreducible uncertainty. It makes us think about selection bias. And these are all things that we should always be thinking about when we're doing an applied econometric analysis. So if there is a lot of noise in the process, then the correlation between D and epsilon will be quite small because epsilon is mostly noise, right? And if there's not very much noise in the process that generates Y, then the opposite would be true. So ultimately, whatever you decide, you need to substantiate with a logical argument. And I view these tools as providing some structure for making that argument in a systematic way. But as a start, if you're using survey data, I would say start with equal correlation restriction and then refine from there if need be. And definitely, we would almost always assume that these correlations have the same sign. So that's why that relationship between the two of them is some number between 0 and 1, not a negative number, because we typically would never assume that there's positive selection on the stuff that I can see and then negative selection on the stuff that I can't see. Of course, that's possible, but probably not likely in most situations. Let's go to another recent or semi-recent paper that improved upon this approach. So this is by Brian Krauth. It's in the Journal of Econometric Methods in 2016. And he introduces a tool called relative correlation restrictions. And this is a generalization of this Altonji-Elder-Taber paper. And basically, he's got a method that he has implemented in Stata, and this will allow the researcher to specify a scalar lambda that governs the relationship between these correlations. And this lambda can be used in two ways. So first, it can be used for partial identification, where I put bounds on lambda, and then I get a corresponding estimate on the alphas. Or, and this is basically the same type of exercise, but different side of the same coin, I can estimate alpha under the assumption that lambda is 0, and then I can find the smallest lambda such that I still have a positive treatment effect estimate. So if there's a treatment effect, then OLS should always be non-zero. And then as I take lambda slightly larger, eventually I'm going to get lambda large enough that my alpha hat is going to be 0. And I'll call that my lambda h. So lambda L is 0, lambda h is this number that makes it so that I have no more treatment effect. And then I can think about, is lambda h big enough to reasonably conclude that there's a causal effect here? So now let's go to another paper that came out in 2019 by Emily Oster in the Journal of Business Economics and Statistics. And in this paper, and I should mention that this paper is also cited even more heavily than the Altonji-Elder-Taber paper, and I think it's because the author implemented a Stata command that practitioners could use. For some reason, everyone gravitates towards this Oster paper when they're applying these methods, and they overlook the Krauth paper, even though I think the Krauth paper is simpler to understand and is just as easy to use. In any case, this paper is also generalizing the Altonji-Elder-Taber approach, and the intuition of this paper is getting back to some of the intuition I shared in the prior video, where we're thinking about how does my treatment effect estimate change as I add more controls, and then how does that relate to the R squared of my outcome equation, with the thinking being that if my selection on observables specification explains 80% of the variation in Y, then I'm unlikely to be confounded by any additional unobservables that are currently unexplained. So the intuition is that if we observed everything that affects Y, we'd have an R squared of 1, but we rarely get to 1. And so how much can we account for by observable selection versus how much would be left for the unobservables to explain? And then the thing to keep in mind here is that if there's measurement error in Y, then the maximal R squared that I could ever hope to achieve is going to be less than 1. And so then I can reason about these things in terms of the maximum R squared. And the implementation is similar to Krauth in that you can do this sensitivity analysis exercise and think about, well, how much unobservable selection would be required for me to overturn my result. So that's just a brief overview of 3 of the main papers that have developed tools for systematically making this evaluation between observable selection and unobservable selection. However, I purposely didn't go into too many details because there's an even newer paper released in 2025 that's not yet published that I believe does the best job to date in systematizing these tools and making it crystal clear where identification is coming from. So we're going to go over that paper in detail in the next video, and in the video that follows that, we'll do a coding demonstration using data from one of my publications to hopefully elucidate how you could apply these methods in your research. So hopefully you're as excited as I am about the stuff that we've talked about now and in the stuff that's coming up in the next videos.